Hello everyone, we are the Team Yangtze. We belong to 3rd year EC department of Thiagarajar College of Engineering. We are here to present a PPT on a research paper which was about MOSFET drain current noise modeling with effective gate overdrive and junction noise. So this research paper was done by these scientists. So let me try to decode some information from the heading itself. So what is MOSFET? MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. It is a type of transistor used in electronic devices to amplify or switch electronic signals. So MOSFET typically consists of 4 terminals: gate, drain, source and a bulk terminal. So drain current. Drain current, also known as ID, is the current that flows from the drain terminal to the source terminal in MOSFET. The amount of drain current is controlled by the voltage applied at the gate terminal. So we move on to noise modeling. Noise modeling of MOSFET is crucial to understand, which predicts the behavior of noise in the device and the overall circuit. Noise can arise from various sources such as thermal fluctuations, carrier generation, recombination process, etc. So effective gate overdrive. So gate overdrive is a term often used in electronics which refers to apply of higher than normal voltage to the gate transistor. So this technique can cause the device to operate faster or achieve different characteristics, but with a caution. It may lead to high power consumption or even damage the electronic component. So junction noise. Junction noise in MOSFET is a type of electronic noise that originates from the semiconductor junctions within the device. So from this heading, we could understand how noise modeling is done with effective gate overdrive and using junction noise. So these are the contents we are going to see in this video. Noise. What is noise? Noise in MOSFET refers to unwanted fluctuations or disturbances in the electrical signal passing through the device. So noise sources in MOS transistors are thermal noise, 1/f noise. So 1/f noise is also known as flicker noise. It dominates at lower frequencies. Noise in the resistive polygate, noise due to the disturbed substrate resistance. And short noise. So short noise arises from the discrete nature of charge carriers, which becomes significant at high currents. So this is the abstract of the research paper. So at source bulk junction and drain bulk junction, there would be a presence of the channel thermal noise and the short noise. So they developed a unified analytical expression for excellent continuity with a smooth transition of drain current noise from weak to strong inversion regimes. So this diagram represents MOSFET channels. So basically there are two types of channel, P channel and N channel. So the P channel MOSFET has a P channel region located between the source and drain terminal. So the drain and source are heavily doped with P region and body or substrate is of N type. So the flow of current would be in the direction of positively charged holes. So as in N channel MOSFET, there would be an N channel region located in between the source and drain terminals. The drain and source are heavily doped with N plus region and the substrate or body are of P type. So here the current flow is in the type of negatively charged electrons. So let us move on to the deep analysis of this research paper. So by including channel length modulation effect and effective mobility, the short channel MOSFET can be expressed as this equation, where K represents Boltzmann constant, VGT is the gate overdrive voltage. So VGT is equal to VGS minus VT, where VG is the gate source voltage and VT is the threshold voltage. So the noise parameter delta is defined as 1 minus u plus u squared by 3 whole divided by 1 minus u by 2. So u is a parameter. U is equal to alpha times VDS divided by VGT, where alpha is known as bulk charge constant. So let us move on to DIBL. DIBL is nothing but drain induced barrier lowering. So it's a short channel effect in MOSFET. Short channel effect in MOSFET refers to the behavior of transistor where the channel length is reduced to smaller dimension. So as channel length decreases, some effects would be prominent. So the reduction of threshold voltage of the transistor at higher drain voltages. So this is known as DIBL.
Hello, my name is Gladson and I will be taking up this session with drain induced brain lowering characteristics. It is a short channel effect in MOSFET referring to reduction in threshold voltage due to higher drain voltages. So we are now going to see about drain induced barrier lowering and long channel. So during this long channel effect, the bottleneck in channel formation occurs far from enough so that it will be shielded from drain combination. So the result will be the threshold voltage will be independent of the drain voltage. So DIBL is very important in this scenario. So since the impact of elasticity, saturation and hot carrier effects on channel thermal noise or counterbalance both can be ignored, and with effective mobility and gradual length mu f and LF effective, so the channel thermal noise of short channel MOSFET will be in drain bias domain will be satisfied. However, it is valid only when in saturation region, which is a strong inversion region, and it will be failed under the condition of subthreshold region, which is weak inversion. So in order to make equation 1 valid in both strong inversion and weak inversion, so modification is needed for the equation VGST effective. So VGT effective will be equal to 2n VTH ln of 1 plus e to the power VGT by 2n VTH divided by 1 plus bracket of 2n divided by theta of n minus 1 e to the power VGT plus minus V2V of divided by 2n VTH, where the theta is equivalent to 1 plus e to the power minus VDH minus VTH divided by 2 delta. Delta is the noise parameter defined here. VTH is the KT by Q thermal voltage, which at room temperature will be 26 millivolt. N is the subthreshold slope factor, whereas in subthreshold linear region occurs with slope, so N is the subthreshold slope factor. V of equal to V maximum of Vt minus subtraction of minus Vt is offset voltage to characterize leakage current at zero gate bias. At zero gate bias, there will be some leakage current, which is also been discussed in the earlier class of BJT. So it is applicable to MOSFET also. So the parameter Vf will be extracted using IV characteristics in subthreshold region. So replacing VGT effective with in 3 with VGT, the single region the channel thermal noises will be given by SID is equal to 4 into delta of KT bracket of W by L effective, which is aspect ratio, into mu effective Cox dash will be the channel's oxidation potential into VGT effective. In strong inversion region, VGS will be greater than VT. So will be the denominator of equation 3 approaches to 1 and numerator of 3 approaches VGT. So 5s will be equation 5 will be strongly equal to equation 1. So in weak inversion, VGS minus VT is less than V2 into VT of. So 1 plus x in denominator of equation 3 approaches x and ln of 1 power e power x in the numerator. So VGT of approaches to the formula of VGT effective is equal to theta of n minus 1 VTH e to the power VGT minus V of divided by n VTH. And channel thermal noise, which is produced, we have already discussed about this, and it will be reduces to the well-known weak conversion noise modulus. SI of D is equal to 2Q I saturation of 1 plus e to the power minus VDS minus VTH divided, it will be the seventh equation, and I saturation will be equivalent to mu effective W by L effective C ox dash n minus 1 into VTH square e to the power VGT minus V of divided by n into VTH, where I sat is the current flat part in the IDS VDS curve. I saturation is already known by yourselves, which is a constant current gain will be after intra saturation region. However, drain current noise behavior will be deviating at RF frequency. At RF frequency, the parasitic effects will be taken into consideration. So this drain current noise behavior will be changed upon that. So Chanitel this demonstrated at the source bulk and drain bulk junction generate thermal fluctuations, which produces drain current noise. It is a channel thermal noise, and it will be amplified by the source bulk and drain bulk junction capacitances. The junction noise produces another plateau, which will be given by spectral density Si of D junction is equal to 4 kT G of SB plus 4 kT G of DB. GSB and DSB were AC conductance of source bulk and drain bulk junctions. Each junction was modeled as a capacitor in series with a resistor R. So G junction, capacitor junction will be equal to omega square C square R divided by 1 plus omega square C square R square. So capacitor and resistor are functions of voltage drop across junction. So capacitor values and resistor values will be changed rapidly across proportional to the voltage applied to the MOSFET. So the SID will be equal to delta of 4 kT W by L effective into mu effective C ox dash of into VGT effective plus 4 kT omega square C naught square R naught divided by 1 plus omega square C naught square R naught square of 1 plus root of psi I plus 1 divided by root of 1 VDS plus psi I. So after this equation, we tried in MOSFET to find out the results. So it will be discussed in the results and discussion session. Figure 1 shows the comparison of the simulated and extracted SID values of 0.13 mm NMOS. So 0.13 mm NMOS is the characteristic of a device which is generated by which is the size of the NMOS transistor design. In weak inversion region, the noise is generated by AC conductance of source bulk and drain bulk dominates drain current noise. So as we can see, this measured is slightly higher than what we have model, which is due to the source bulk and drain bulk regions domination. So that's it, and it will be continued by Ashok further. Thank you.
In this figure, the graph has been plotted for the first order derivative of the drain current noise versus the gate bias voltage characteristic of 0.13 micrometer NMOS. This graph shows the comparison of the first order derivatives of drain current noise between the model and experimental data shown from the weak inversion to strong inversion region. this model exhibits a smooth transition at the boundary of the regions, and it emphasizes the model accuracy and continuity in the MI and WI regions. The advanced feature of the model makes it very attractive and promising in circuit simulation, since the region is becoming more important for low voltage and low power circuit application. And in the graph, this graph is linear up to the moderate inversion region and then constant in the strong inversion region. Then in this graph, the graph is measured and modulated the drain current noise versus the drain bias voltage characteristic of 0.13 micrometer in MOS, and this graph shows the drain bias dependence of drain current noise in strong inversion region, that is due to the noise factor and short channel effects discussed in previous session. And in the moderate inversion region, the channel thermal noise decreases with VDS when the operation point is translating from the linear region to the saturation region. In figure 4, the graph is plotted for drain current noise spectral density versus the gate bias voltage of the NMOS with different gate lengths of 0.13, 0.25 and 0.5 micrometer. In the subthreshold region, the transconductance decreases exponentially as the gate bias decreases while the drain current noise saturates, resulting in an exponential increment of thermal noise excess factor. The simulated result has excellent agreement with experimental data, indicating that the model is scalable across different gate lengths and is valid from WI to MI to SI regions. Finally, in this figure, the graph has been plotted for the measured and simulated thermal noise factor versus the gate bias voltage characteristics of NMOS with different lengths of 0.13, 0.25 and 0.5 micrometer, and this graph shows that the drain current noise and the thermal noise excess factor is for NMOS with the different lengths. The noise performance of device improves when the operating point moves from strong inversion to weak inversion region. However, thermal noise excess factor becomes large when device operates in the sub-threshold region. The conclusion of this paper tells about the introduction of an effective gate overdrive, which includes the noise parameter that allows channel thermal noise being modeled accurately across the drain bias for WI, MI and SI regimes, and with the incorporation of the junction noise, the accuracy of the subthreshold drain current noise model improves tremendously. The continuity and the smoothness of the proposed model have been demonstrated with continuous partial derivatives. And finally, this model has unified expression for all regions and successfully verified with excellent match to 0.13 micrometer technology. These are the references for this paper. Thank you.